Okay, in this video we're going to talk about the internal energy, and in the next one we're going to combine internal energy and work and then come up with our first law of thermodynamics. Okay, so internal energy is the sum of the kinetic energies plus the potential energies of all the particles, okay, of a system. Alright, now we will be interested in ideal gases, okay, and in fact within this category of ideal gases we'll also be interested in what's the word for it, monatomic ideal gases. Okay, now for a monatomic ideal gas, if you recall, the internal energy is dependent on the temperature of the gas. It is given by the expression 3/2 nRT. Okay, where T is the temperature in Kelvin, N is the number of moles, and R is the gas constant. Okay, so when the temperature changes from one point to another, so if T changes, okay, from say T1 to T2, then we can find the internal energy for the gas, the change in the internal energy, delta U, which will be equal to U2 minus U1, and this is simply 3/2 nRT2 minus 3/2 nRT1, okay, and that if we factor out the terms 3/2 nR, we end up getting T2 minus T1. So this is the change in the internal energy of the gas. Alright, so in order to calculate the change in the internal energy, all you need to know are the temperatures. Okay, and this is all for a monatomic ideal gas. That's all it depends on, nothing else. So if you know the temperatures at different points, then you can figure out the change in the internal energy. Now, there are processes where the internal energy does not change. Okay, namely, this process essentially is called an isothermal process. So if the process is isothermal, then that implies that T remains constant. Okay, and which in turn implies that delta U equal to 0. So in an isothermal process, the internal energy of the gas does not change. It remains fixed. Alright, great. So we have that. Now, let us apply this idea to a couple of simple situations. Okay, once again, we'll do it in the context of thermodynamic processes where, we'll take objects going from one process to another. So we'll go back to our original curve where we had a PV diagram. The pressure went from P0 to V0, and then it went to 3P0, and the volume increased to 3V0. And we can ask for this process A to B, what is the change in the internal energy? And let's assume that you're given, say we have N moles of the gas. N moles of the gas. Okay. Right. So let's see how to figure this out. Now, if you look at this problem, okay, first of all, try doing this yourself. See what you come up with. Okay, if you get the answer to this, great. If not, just pause, do your work, and then check with whatever I have. Okay. Before you do it, I'll give you one hint though. Here, the answer will be in terms of only P0, V0. Okay, so the T itself will not be there. So think about it and see what you get. All right. So I will move on with the work though. Alright, so in this problem, since you've been given P0, V0, and since you've also been given the number of moles of the gas, alright, we can find the temperature, okay, by using the ideal gas law. And this is something that you will use a lot. The ideal gas law states that PV equals nRT, okay, so we can use this formula to figure out the temperature in state A. So in state A, my T A is going to be equal to P0 V0 divided by nR, and in state B the temperature is going to be equal to 3 times P0 because that's the pressure, the volume is 3 times V0, and divided by n times R, which happens to be 9 P0 V0 divided by nR. Great. So now that we have the temperatures, calculating the change in internal energy is really easy. So delta U for the process A to B, and again we have to keep the order intact, okay, because you see in this process you go from A to B, you go from PO VO to 3PO 3VO. If you were going in the opposite direction, then the sign is going to be different. So delta UAB for this process is going to be equal to 3/2 NR, okay, times TB minus TA. Very good. So let us substitute for each of the terms. So it will be 3/2 NR. TB is equal to 9 P0 V0 divided by NR minus P0 V0 divided by NR. Okay, so this is equal to 8 P0 V0 NR, and so we have 3/2 NR times 8 P0 V0 divided by NR, and you see the NRs cancel out. Okay, well, the 2 gives me a 4, and 4 times 3 is 12 P0 V0. So this is the change in the internal energy for the gas. Alright, so that's what you do. Now, I want to point one thing out here. The U is only dependent on the temperature. Okay, for the monatomic ideal gas. For ideal gases, that's what it does. It depends only on the temperature, and as a result, okay, for a cycle, okay, which means you take a gas in state A, you take it through some cycle, and you bring it back to state A. Okay, and when you bring it back to state A, you bring the temperature back to what it was. So for a cycle, delta U is equal to 0. So this is very important. Keep this in mind, because we'll be dealing with cycles a lot. So delta U is equal to 0 for a cycle. So when you take a state from one step to another and bring it back to its original state, okay, the effective change in the internal energy is 0. That doesn't mean that the internal energy has not changed during the process. It has changed, but it gains some internal energy at some point, and then it loses it. And so the effect of the net change in the internal energy for a closed cycle is always equal to 0. Okay, so that's all the things that you need to know about internal energy. Keep in mind, for a monatomic ideal gas, the internal energy is 3/2 nRT. And the change in internal energy is 3/2 NR delta T. To find the internal energy for processes, remember, always rely on PV equals nRT, because especially if you're not given the temperature directly, you can find the temperature very easily. And then the next thing you need to know is that for a cycle, the change in the internal energy is 0. Okay, so this is all that you need to know about internal energy. We are going to move on. In the next video, we're going to discuss the first law of thermodynamics.